Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 26 of Algebraic Topology. In previous lecture we saw some topological results and we defined projective spaces and then we discussed this phenomena of attaching a cell, and later on we proved that projective spaces can be obtained by attaching different cells. So in today's lecture our main emphasis is going to be the effects of attaching cell to the calculation of homology, and we shall see that attaching cells really help us out in calculating the homology. So in today's lecture first we will see some general result, and then we will continue with the calculating homology of different spaces based on this result of homology and attaching cells. So let's continue with today's lecture. Let's recall ourselves about the definition of attaching cell. So before going to the definition of attaching cell, we need this definition of co-product of two topological space. So if x1 and x2 are two topological spaces, then we can define the co-product x1 union x2. Okay, so it's a special union, but I'm going to say it union. Okay, so x1 union x2 is disjoint union in which x1 and x2 are open sets. Okay, so it's a topological space where x1 and x2 are open sets. And then we can also define continuous functions from this co-product of x1 and x2 to y. Okay, so it's defined like we need a continuous function from x1 to y, and we need a continuous function from x2 to y, and using those two continuous functions we can define a continuous function from the co-product of x1 and x2 to y. Now let's see how we attach two spaces via a map. So it's a very simple procedure. Suppose I have a space y and a space x. So the procedure for attaching the space x with y is very simple. So choose a subset A, closed subset A of x. So let's assume this circle is basically closed subset A of x. Then define a map from A to y. Okay, so let's assume this this closed curve is image of this circle inside y. Then what we do is we take this point A of A and attach it, okay, glue it with this point f of A of f of capital A. Okay, so in the image of A under this map f, so we glue these 2 points. Similarly, if there is a point B, then we glue it with this point f of B, and similarly we just glue the corresponding points. So just glue the element with its image inside f, inside y. Okay, so when we glue, then we get an image like this. So basically we glued this closed subset A of x with its image under this continuous map f. Okay, so let's see how to define it mathematically. So if we have two spaces and A is a closed subset of x, and we have a continuous map from A to y, then how we glue them? Okay, so far we haven't said anything very difficult. So the next part is the gluing thing. So how to define this gluing topologically? So we take the co-product of x and y, okay, and then we take its quotient with this equivalence class. So what are these equivalence classes? So the elements A and f of A are same in this equivalence class, so they are equivalent to each other. So in other words, we can say that A and f of A are same because we are taking quotient with this. Okay, so that's how we define it precisely. So that's how we attach a space x to the space y using this map f. Okay, For our next discussion, we need the following definition. An N cell is a homeomorphic copy of the open N disk Dn minus Sn minus 1. So if you remember, Sn minus 1 lives inside Rn and Dn lives inside Rn, and basically the boundary. Okay, so we mostly we denote this partial sign, okay, to denote the boundary of some object. So boundary of Dn is basically equal to Sn minus 1. Okay, so if we just exclude the boundary, then the rest of the disk is basically an open end disk. So for example, observe this diagram where we have considered D2 minus S1, and S1 is the boundary of D2. S1 is a circle in plane and D2 is a disk in plane. Okay, so when you take out the boundary, then we get an open 2 disk. Okay, so our next definition is given any Hausdorff topological space and a continuous function from Sn minus 1 to y, then we can attach this disk Dn with y. Okay, so how we do that? Because if we have a disk, okay, Dn, of course I'm just depicting the diagram for two-dimensional case. Okay, so let's consider this is Dn. Okay, and in this case this is our space X, and let's say we have a space Y. Okay, and over here Sn minus 1, which is inside Dn, is closed subset. Okay, so what we need is, if we want to attach the space X to Y, we need a continuous function. So here it is, we need a continuous function f from Sn minus 1 to y. Okay, so in other words, we have a continuous function from this boundary of Dn to y. Okay, so once again, let's assume that this is the image of Sn minus 1 inside y. So the next thing is gluing this Sn minus 1 with its image inside y. Okay, so of course we know that how to do that, because just take the co-product of x and y. So in this case x is Dn, so just take the co-product topology of Dn and y and glue it using this map f. Okay, so basically Dn co-product y quotient with this equivalence relation, and this equivalence relation identifies the points on this Sn minus 1 with its images inside y under this map f. So once you glue them, so you will get something like this. Okay, so after gluing you get an image like this. So this is your space after obtaining this cell N cell Dn with y. Okay, next we are going to see that how this procedure of attaching a cell helps us out in calculating the homology. Okay, so consider this space yf, and we have seen that, we have already seen it, that what is yf. So basically this is equal to attaching an N cell with y via this map f. Okay, so where y is of course a Hausdorff space, so this was the condition of attaching this N cell with y. Then there exists an exact sequence, and this exact sequence is going to help us in calculating the homology of this space yf. Okay, so what are the reasons for this exact sequence? So we are not going into the detailed proof of this theorem, and I'm just going to tell you the motivation behind this exact sequence. So we know that we can attach this Dn with y if I have a continuous function from Sn minus 1 to y. So there exists a continuous function f from Sn minus 1 to y, and if there exists a continuous function, we have already seen it many times, that it will give me maps between the homological groups of these spaces. So we have these maps and we denote these maps with F lower star. And the next thing to notice is this Y is included. Okay, so there is an inclusion of this Y inside Dn glued with Y. Okay, so what is this inclusion? Let's go back and see pictorially. So observe that we just attached this space X with this space Y, and we haven't deleted anything from Y. The only thing we are doing is we are identifying some points of Y with some points of this Sn minus 1. So identifying doesn't mean that we are deleting those points. So those points are there. So in other words, we can say that Y lives inside attaching this N cell with Y. Okay, so this is Y under the map F. So Y is included inside this space. Okay, so we have an inclusion, and if we have this inclusion, it's a continuous map. So in other words, we can say that it induced the following maps between the homological groups. Okay, so due to the continuous function from Sn minus 1 to Y, we have these maps between the homological spaces, and due to this inclusion we have the following maps between the homological groups. Okay, and using this, now we are going to see that how this is going to help us in calculating the homology. Okay, so our next corollary is very important, and basically it's an easy consequence of the previous theorem, but unfortunately we are not going to see the proof. So the corollary says that the top homological groups, apart from the top homological groups, so the rest of the homological groups of Y and YF are isomorphic. So in other words, when we are attaching a cell to a space Y, then if we know apart from the top two homological groups, if we know the rest of the groups of Y, then it will help us in calculating the homology of this space YF, which is obtained by attaching a cell with Y. And the next thing is, if we consider this exact sequence, then the last map is a surjection for n greater than or equal to 3. Okay. Now let's go on with the applications of this theorem and its corollary, and let us see that how this is going to help us in calculations of homology. So our first example is a very simple example where we attached an n plus 1 cell to Sn. So how we do that? Okay, so if we want to attach a cell with Sn, then I need a continuous function from Sn to Sn. Okay, so this Sn is due to the fact that we want to attach n plus 1 disk. Okay, and this Sn is due to the fact that we are attaching n plus 1 disk with Sn. Okay, so we need a continuous function from Sn to Sn. Okay, so that's what it says. If we have a continuous function, and this continuous function is a very special continuous function, we took the degree of this continuous function to be d. So why we are taking this? Because if we consider this special continuous function, then this is going to help us in calculations of some further homological spaces. Okay, so this is a continuous function of degree d. So in other words, we can say that d points of this Sn are going to 1 point of this Sn. Okay, and if we have this map, then according to our previous definition, we can attach an n plus 1 cell with Sn. So taking the co-product of dn plus 1 and Sn, and identifying and gluing them along this map F. Okay. Now let's see how this will help us in calculations of homology. So consider this exact sequence. So consider the case when n is not equal to 0. Okay, and then start from hn plus 1. Okay, so Sn. Okay, so this map F is from Sn to Sn. So basically we are going to take it from Sn to Sn. Okay, and of course this Sn and this n, they are the same, so we are calculating the homology of this C for this special homological index. Okay, so and this goes to hn plus 1 to C, and this goes to hn Sn, this goes to hn Sn, and this goes to hn C, and this goes to hn minus 1 Sn, up to so on. So we know the homology of a sphere. Okay, so according to our previous discussions, so hi of Sn, so this is equal to z if I is equal to 0. So why is this the case? So of course we are considering n is not equal to 0, because when n is equal to 0 then it is not path connected. So for n not equal to 0, the homology of the sphere is going to be equal to z, because it is path connected, and this is going to be equal to z again when I is equal to n, and this is going to be equal to 0 otherwise. Okay, so using these homological groups of the sphere, we see that this is going to be 0, and this is going to be 0, and this is also going to be 0. Okay, and what about this map between hn of Sn to hn of Sn? So this is the map. So if we have this continuous function f from Sn to Sn, which is a function of degree d, then this map, okay, so hn Sn is basically z, and hn Sn is z. So this map from z to z is basically multiplication with d. Okay, so you multiply integers with d and you obtain the elements of this set. Okay, so that's what we have as map between these two homological groups if f is a continuous function of degree d from Sn to Sn. Okay, so this implies, so this whole discussion implies that we have the following situation. Okay, so starting from 0, so everything else on the left is 0, so 0 to hn plus 1 C goes to z, goes to z, goes to HNC goes to 0, and this map is basically multiplication with D. So the image, so it's an exact sequence, because that's what the theorem says. Okay, so if this is an exact sequence, then the image of this map is basically equal to the kernel of this map. So the image of this is 0, so that's why the kernel of this map is 0. So in other words, this hn plus 1c is embedded inside z. Okay, so and then the image of this map is equal to kernel of this map. Okay, but the kernel of this map is basically 0, because we are just multiplying with d, and the only way we can get a 0 in the image is that we multiply 0 with d. Okay, so in other words, we can say that the image of this which is hn plus 1c itself, so the image of this is equal to kernel of this. So in other words, this implies that, okay, so hn plus 1 of c is equal to 0. Okay, so this whole discussion leads us to the following thing. So 0 goes to z, goes to z, goes to HNC, goes to 0. Okay, now we have the following sequence, basically it's a short exact sequence, H and C is to 0, and this map is basically multiplication with D. Okay, now let's calculate this H and C using this map. So the point is the image of this is 0, which should be the kernel of this, so this Z is contained inside this, and then the image of this is basically DZ. Okay, so the image of this is DZ, that is equal to the kernel of this map. So let's call this map H, and the kernel of H is equal to DZ. Okay, so if we know the kernel, and we also know that this is going to be this H is going to be an onto map. So why is this the case? Because the image of H is equal to kernel of Hn plus HNC. So the kernel of this map is basically the whole HNC. So in other words, we can say that this H is onto, so also H is onto. So given these two facts, we can say that H and C is isomorphic to Zn quotient with the kernel of H, but the kernel of H is dz. So in other words, we can say that this is equal to this Zd. Okay, so so far we have calculated the homology of C for n. Okay, so for I is equal to n. Okay, so where n is the same as this Sn. Now let's calculate what's going to happen when I is equal to 0. So for I is equal to 0, so this C is basically path connected. Okay, so if it is path connected, then we can say that this H0 of C is basically going to be equal to Z. Okay, so so far we have calculated the homology when I is equal to 0 and I is equal to n. So what about the rest of the homological groups? So let's consider this sequence. So HISN goes to HISN goes to HIC goes to HISN. Okay, HI minus 1 SN goes to HI minus 1 SN, up to so on. Now the point is, this is 0 as long as I is not equal to 0 and n. Okay, so and this is also 0. So if we have 0 on both sides, then this implies that HI of C is equal to 0. So we have calculated the homology of this space C obtained by attaching n plus 1 disk with this sphere Sn. Okay, so the homology of this space C using only the theorem is basically equal to, so when I is equal to n, okay, when I is equal to, okay, sorry, when I is equal to n, then this is basically equal to Zd. When I is equal to 0, this is Z, and this is 0 otherwise. Okay, so using our theorem, we calculated the following homology of the space C. Now based on this example, we have this important question. Okay, so the question is, given any finitely generated abelian group, can we find a space MAN? So it depends on this finitely generated abelian group A and this N. Okay, so we have two inputs, this finitely generated abelian group A and N. Can we find this space such that this is Z when I is equal to 0, this is A when I is equal to N, and it is 0 otherwise? Of course, you can observe that we have generalized the homology of C, which was ZD when I is equal to N, and it was Z when I is equal to 0, and it was 0 otherwise. So can we generalize this thing to any group? Okay, so we also know that every finitely generated abelian group is product of these finite cyclic groups. Okay, so can we do that? So this is not part of your course, but it will be very interesting. It will help you learn things further if you can try to answer this question. So let's continue with our further examples, where we are going to use attaching cells and the theorem that we presented today, and we are going to use those things to calculate the homology. Okay, so our next example is the calculation of homology of real projective plane. Okay, so what is a real projective plane? So we have already seen that a real projective plane is basically the space of all lines in three-dimensional space. Okay, so observe that we are talking about projective plane and we are taking lines inside three-dimensional space. Okay, so one-dimensional high. Okay, so in other words, if this is three-dimensional space, then I need a space which represents set of all lines passing through origin. Okay, so one way to do that is to consider upper hemisphere and take the intersection of all these lines with the upper hemisphere. Of course, you can easily notice that we need to include this circle, which is the base of this hemisphere as well, but we need to include half of this circle, because otherwise we will get once again repetitions of the lines in plane. Okay, so in other words, I'm just saying that in xy plane, if I want to consider the lines inside xy plane, then I just need to take half of the circle, because if I take the full circle, then one line will be represented twice. And once again, going further down, I just need to include one point of this semicircle, so the boundary of this semicircle, because once again, if I include both these points, then I'll be including this x-axis twice. So we have this upper hemisphere. Now the point is, I can easily define an homeomorphism from this hemisphere with this disk D2. Okay, so what is this object? Okay, so I can take this object as the following. I'm attaching D2 with S1. So I have this circle, and I can define a map to another circle. Okay, so this circle is basically the boundary of disk D2. Okay, so I'm defining a map from the boundary of this disk D2, which is S1, to another circle S1. Okay, so if we have a continuous function from this S1 to this S1, then I can attach this D2 with S1, and at the end I will get this object. So which we have already seen that it's going to be topologically, this is going to be real projective plane. Now let's see how to calculate the homology of this real projective plane. So as I have discussed earlier, what do I need? I need a continuous function from S1 to S1 of degree 2. Okay, so continuous function of degree 2. Okay, so if I have this thing, then I can attach D2 with S1, which will give me a real projective plane. So in other words, I am attaching, okay, so we are attaching D2 with S1. Okay, and we will obtain real projective plane. Okay, so in other words, real projective plane P2R is nothing but attaching D2 under this map F with S1. So in other words, if we want to calculate the homology of this P2R, we should understand the homology of this space, but we have already calculated the homology of this space. Okay, so we remember that we calculated the homology of space C, which we obtained by attaching an n+1 cell with Sn. Now we are attaching a 2 cell with S1. So in that case it was a degree D map, in this case it's a degree 2 map. So P2R is a special case of C. So what is C? So attaching an n+1 cell with Sn under this map F, where F is degree D, where F is degree D. So we have calculated the homology of this C as the following. So this is equal to Z if I is equal to 0, it is path connected. This is ZD if I is equal to N, okay, and this is going to be 0 otherwise. Okay, so this thing implies the homology of real projective plane. Okay, so in this case N is equal to 1. Okay, so for I is equal to 1, we can say that this is ZD, it's a degree 2 map, so basically this is Z2. For I is equal to 0, this is Z, so for I is equal to 0, this is Z, and this is 0 otherwise. So that's how we calculate the homology of a real projective plane in a very simple way. So let's continue with the calculations of homology for higher dimensional real projective spaces. So remember that we can obtain an n-dimensional real projective space by attaching an n cell with n-1 dimensional projective space. So in other words, what we are saying is, if I have a 3-dimensional real projective space, then I can obtain it as by attaching an n cell with 2-dimensional real projective space, of course along some function f. Okay, so in order to do that, what do I need? So I need a function f from the boundary. Okay, so in this case, this is 3, so I need a function from the boundary of D3. Okay, so what is the boundary of D3? This is going to be S2, so I need a continuous function from S2 to P2R. So if I have a continuous function from S2 to P2R, then I can attach D3 with P2R, and if I can attach this thing, I can define P3R. Okay, so let's see how we can use this discussion to calculate the homology of P3. So 3-dimensional real projective space, so P3R, we have seen that this is equal to attaching D3 along some continuous function with P2R. Okay, so where f is a function from the boundary of D3, so what is the boundary of D3? It is S2, so we should have a continuous function from S2 to P2R. Okay, so to calculate the homology, we don't need to know this function f. Okay, so the only thing we need to know is we have a continuous function from S2 to P2R, and using this we can attach D3 with P2R, and we will obtain P3R. Okay, and there is an inclusion in this case. Okay, so just compare this situation with the following situation, where we consider Sn-1 to y and then to yf, and where yf is equal to dn glued along f with y. Okay, so in this case this was inclusion, so that's the same as here. Okay, so we have this sequence of S2, P2R and P3R. Now we are going to use this sequence to calculate the homology of this 3-dimensional real projective space. Okay, so to calculate the homology, we start from the following thing. Okay, so we start from H4 of S2, this goes to H4 of P2R, this goes to H4 of P3R, and this goes to H3 of S2, which goes to H3 of P2R, and which goes to H3 of P3R, and this continues to H2 of S2 to H2 of P2R, and which goes to H2 of P3R. Okay, and going on to H1 of S2, which goes to H1 of P2R, and which goes to H1 of P3R, and which goes on to H0 of S2, which goes to H0 of P2R, which goes to H0 of P3R, and which goes to 0. Now let's see how many homological groups we know here. So we know the homology of sphere, so HIS2, so this is equal to Z when I is equal to 0 or 2, and this is 0 otherwise. We also know the homology of real projective plane. So the homology of real projective plane is HI of P2R, so this is equal to Z when I is equal to 0, this is equal to Z2 when I is equal to 1, and this is 0 otherwise. Okay, so we can say that this is 0, H3 of S2 is 0, H2 of S2 is Z, H1 of S2 is 0, and H0 of S2 is Z. Coming to the homology of real projective plane, H4 of P2 is 0, H3 of P2 is 0, H2 of P2 is 0, H1 of P2 is Z2, and H0 of P2 is Z. And similarly we can also say that H0 of P3R is going to be path connected, so this is Z. So the only homological groups that we need to calculate for three-dimensional real projective space is this, 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 and this one. So 1, 2, 3, 4 dimensional. So the four-dimensional, so H4 P3. Okay, so this is easy to calculate. So why it is easy to calculate? Because there are zeros on both sides, so we can say that this implies, okay, so we have H4 of P3R is 0. Okay, okay, so this is 0. What about H3 of P3R? Okay, so this third homological group of this P3R is going to be Z, because there is 0 over here and there is 0 over here. So in other words, this map is an isomorphism, so we can say that H3 of P3R is going to be equal to Z, so isomorphic to Z, to be very precise. So this is done and this is done. Now let's see how to calculate H2 of P3. So once again, there are zeros on both sides, so we can say that, so which implies, so H2 of P3R is basically equal to 0. So this is also done. Now the only thing left over here is H1 of P3R. Okay, now we are going to use a trick from homological algebra, and which says that I can cut this exact sequence over here Okay, so I can cut it from here and I will continue with just 0. Okay, because in this case the further sequence is Z, Z and Z. Okay, so in other words what I will get is the following thing. Okay, so Z2 goes to H1 of P3 goes to 0, and this is also coming from 0. So what we get is the following. So 0 goes to Z2 goes to H1 of P3R goes to 0. Okay, and of course this implies that this first homological group of three-dimensional real projective space is Z2. Okay, so we can observe that we have calculated all the homological groups of this three-dimensional real projective space. Okay, so this is Z when I is equal to 0, this is Z2 when I is equal to 1. Okay, so let's see what were the other homological groups. So when H3, okay, so this H3 is also Z. Okay, so in other words when I is equal to 1 or 3, this is Z, and this H2 is 0 and H4 is 0, so basically it is 0 otherwise. Let's continue with our next example, where we will calculate the homology of complex projective spaces and quaternionic projective spaces as well. Okay, so we know what is a complex projective space. So basically this P and C is basically take C and plus 1, take this 0 out and take its quotient with the following equivalence relation, and the equivalence relation is A naught up to A n plus 1 is equivalent to B naught up to B n plus 1 if there exist lambda belongs to C star such that this A naught up to A n plus 1 is equal to lambda times B naught up to B n plus 1. So we are doing exactly the same thing as we did for real projective spaces. So basically what we are doing is we are taking space of all one-dimensional vector spaces inside this n plus 1 dimensional vector space. More geometrically, basically we are taking the space of all lines passing through the origin. So this P and C will represent set of all lines passing through the origin. Okay, so basically we are taking out this origin because this origin belongs to each and every line, and if we include this origin, then this will collapse this quotient to just one point. So that's why we are taking out this origin. Okay, so this equivalence relation says that two points are equivalent if they are scalar multiple of each other. In other words, we are saying that two points are similar or equivalent if they are on the same line, because points on the same line are scalar multiple of each other. Okay, so that's what is the definition of n-dimensional complex projective space. Let's see how to calculate the homology of this space, of this projective space, using today's results. Okay, so in general we are going to use induction in this case, but let's see how we calculate it. Okay, so when n is equal to 0, for n is equal to 0, this is just going to be 1 point, because when n is equal to 0, then what we are doing is we are taking P0 C is basically equal to 0 plus 1 is 1 minus the origin and take its quotient with the equivalence relation. A is equivalent to B if there exists lambda such that A is equal to lambda C. A is equal to lambda B. So of course we can see that any two complex numbers are equivalent. So this is just going to be 1 point. Okay, and we know the homology of 1 point, that for 1 point we always get, okay, so Z. Okay, so for p is equal to 0 we have Z and it is 0 otherwise. Okay, so in other words, HP of P naught of C is equal to Z when P is equal to 0 and this is 0 otherwise. Now assume the statement is true for n, and we want to show the result for n plus 1. Okay, so in other words, we assume that HP of P and C is equal to Z if P is equal to 0 to 4 up to 2n, and this is 0 otherwise. And what we want to show, so to show is that HP Pn plus 1 C, so this is equal to Z if P is equal to 0 up to so on 2 n plus 1, and this is 0 otherwise. Okay, now the first thing to notice is we obtain Pn plus 1 C. Okay, so we obtain Pn plus 1 C from PNC by attaching a 2n plus 2, which is basically I'm just taking 2n plus 1. Okay, so 2n plus 2 cell. Okay, so that's how we obtain Pn plus 1 C from PNC. Okay, so if we obtain Pn plus 1 C from PNC by attaching a 2n plus 1 cell, then by the corollary of our today's theorem that we are using again and again, so that corollary says that apart from the two top homological groups, rest of the homological groups are going to be isomorphic. Okay, so in other words, we say that apart from the groups 2n plus 1 and 2n plus 2, the rest of the homological groups are going to be isomorphic. So we need to show, so we only need to show, so we need to show or calculate, okay, calculate the homology of P n plus 1 C for P is equal to 2n plus 1 and P is equal to 2n plus 2. Okay, so that's what we want to show, because the corollary says that the rest of the homological groups for PNC and Pn plus 1C, so this n-dimensional complex projective space and n plus 1 complex projective space, so they are isomorphic otherwise. Okay, now if we are obtaining this Pn plus 1, so n plus 1 dimensional projective space from n dimensional space by attaching a 2n plus 2 cell, then we should have a map from the boundary of this 2n plus 2 disk. Okay, so what do we have is, so this attaching result requires that we should have a map from S2n plus 1 to PNC. Okay, so this is our continuous function, and of course this is included inside this n plus 1 projective space. Okay, so using this we consider the following exact sequence. So 2n plus 1 goes to H 2n plus 2 PNC, this goes to H2n plus 2 Pn plus 1 C, and this goes to H2n plus 1 of S2n plus 1, and this goes to H2n plus 1 PNC, and this goes to H2n plus 1 Pn plus 1 C, and this goes on to H2n S2n plus 1 up to so on. So we know the homology of sphere and this n-dimensional projective space. So the homology of sphere implies that this is 0 and this is z, and we also know that this is going to be 0 because it says that this is z only till 2n, and this is 2n plus 2, and from once again from the same result we see that this is 0 and this is also 0 from the homology of sphere. Okay, so this implies that H2n plus 1 of this n plus 1 projective space is going to be equal to 0. Okay, and also there are zeros on this side and this side, so basically this implies that we have the following exact sequence. So H2n plus 2 of Pn plus 1 C goes to Z goes to 0, and from our discussions of homological algebra, this says that these two are isomorphic, so this implies that H2n plus 2 of Pn plus 1 C is going to be equal to or isomorphic to Z. Okay, so once again what we needed to calculate, so we needed to calculate the homology of this n plus 1 complex projective space for this value and this value. Okay, so so basically this value doesn't belong here, so we needed to calculate this homology from 2n plus 1 and 2n plus 1. Okay, so we have calculated the homology. This is the homology when p is equal to n plus 1, and this is the homology when p is equal to 2n plus 2. So that's our homology of complex projective space. So we used induction to calculate the homology of complex projective space. Similarly, exactly on the same lines, we can calculate the homology of quaternionic projective spaces. So in that case you can guess that what we are going to attach. So use our previous lecture's discussion about the quaternionic projective spaces. So in today's lecture we have seen that an important result and its corollary which helps us in calculating the homology of attaching cells. Okay, so after attaching cells we obtain some topological spaces, and the homology of those spaces is easy to calculate if we know this theorem and its corollary. And using that, we calculated three important examples, where the first example helped us in calculating the homology of real projective plane, and then we calculated the homology of three-dimensional real projective space as well, and then we continued to calculate the homology of all projective spaces. So notice that we didn't calculate the homology of higher dimensional real projective spaces. We shall see that we need some other results to calculate those homologies, and for the homology of complex projective spaces it was easy to calculate, and that's what we calculated in today's lecture. And also using the same discussion we calculate the homology of quaternionic projective spaces. Next time we will continue our discussion with this chapter of cellular homology, and of course we haven't yet started the definition of cellular homology and its basic ingredient CW complexes, but we shall start our discussion on these topics in our next lecture. This is the end of the lecture. Thank you very much, and Allah Hafiz.